right, so we're looking at section 4-5, and in this section, we're going to be kind of bringing together a lot of the tools that we've gained over the last few sections and working with exponential and log equations. So we're going to need those expanding and condensing properties. We're going to need evaluating exponential and log expressions. We're going to need algebra, the X method, and solving equations, and we're going to need to check our answers. So these are the four different kind of approaches, big picture approaches to the different types of problems that we're going to do. So the first tool here we have is if my base here and my base here are the same, then that means my exponents also must be equal. So if this side is equal to this side, my bases are the same, my exponents must be the same. Here, if I have the log base b of one side and the log base b of the other side, similarly to what we just saw, if I have the log of one side and the log of the next side, then that means these pieces must be equal. We can also use the Snail Rule. If we have one logarithm on one side, we can turn it into an exponential equation. And we can also take the log or the natural log of both sides of an equation. So those are going to be the different things we're able to do in these equations. And when we're working with these types of things, we want to make sure that when we're solving the exponential equations, we want both sides in the same base, and then set the exponents equal to each other. That's what we were just talking about here. And what we also want to make sure we do is check our answers, especially with logarithms, because we can't take the log of a negative number or of 0. So we always have to check our answers, always. With exponential functions, remember with an exponential function, there's no restrictions on your domain. So you can plug in, negative numbers and all of that, and that's perfectly fine. It's with logarithms that we really have to be careful. So looking at our first example here, we have 5 to the power of 3x minus 6 equals 125. And this kind of looks like this setup here, but my bases are not the same. But I can rewrite 125 so that it's base 5. So I can rewrite this as 5 to the power of 3x minus 6 equals 5 cubed. 125 is 5 cubed. Now my bases are the same, so my exponents have to be equal. And I can add 6 to both sides, and x equals 3. Not too bad. Number 2, 8 and 4 look like maybe we could rewrite them the same way, but we can't rewrite 8 as like 4 to some power. 4 to the first power is 4, 4 squared is 16, so that's not going to work, but we can rewrite both of them. 8 can be rewritten as 2 to the third power, and 4 can be rewritten as 2 to the second power, and now they have the same base. But remember, they already have the exponents that are on them, and so we need to rewrite those now, multiplying here. So we have 2 to the power of 3x plus 6, multiplying there, equals 2 to the power of 2x minus 6. And so now we want to set those exponents equal to each other and solve. Oops, this should be a minus 6. So I can subtract 2x from both sides, and I can subtract 6, and those cancel, I'm left with x is equal to negative 12. All right. Now this next one looks like the setup is the same. The difference with this one is that there's no way for us to rewrite 134 as 5 to some power. So we're going to have to try something different. Now, what we can do is looking at our different tools up here and see if there's something else I can do. Now, I don't have a log on each side, so this is not going to help me. I don't have a log at all, so the Snail Rule is not going to help me. But we can take the log or the natural log of both sides. So I'm going to go ahead and do that. And just for the sake of practicing natural log, I'm going to take the natural log of both sides. And when I do that, that x can come out front. So I have x natural log of 5 equals the natural log of 134. I only have one x, and whenever we're solving, all we're trying to do is getting x by itself. So I'm going to divide by this number. The natural log of 5, if we plug it in our calculator, we just get a decimal. So this just represents a number. So that cancels out, and I'm left with x is equal to the natural log of 134 over natural log of 5. This is our exact answer. We have an equal to sign there. And as soon as I type it in my calculator, it's now an approximation. So it's no longer an exact answer. So typing that in my calculator, the natural log of 134 divided by the natural log of 5 gives us 3.04. So again, that's an approximation there. All right, we can take a look at the next one, and I'm not seeing a way for us to rewrite this. I could rewrite 8,000 and try to play with that a little bit. We could say, okay, well, let's see, that's 8 times 1,000, and 8 times 10 to the third power, that's 1,000. But that still doesn't fix it because I have an 8 out front there, not just the same bases. So this isn't going to actually help me. What I can do is take the log of both sides. And since I did natural log here, I'm going to go ahead and do regular log here. And I'm actually going to do regular log for a few reasons. So I have the exponent here that I can pull out front. And remember, if we don't have a number down here, that means it's base 10. Well, if these two numbers are the same, this is equal to 1. So x is already by itself. And here I have log of 8,000. And technically you could leave it that way, but remember what we just did. This is the same thing as 8 times 10 to the third power. So we could actually expand this. And this 3 could come out front. And remember, log base 10 of 10 is just 1, and 3 times 1 would just be 3. So we could just leave it like that. But this is fine, or you could rewrite it like this. And then again, you could type it in your calculator. So when we type it in our calculator, it's no longer an exact answer. Now it's going to be an approximation. And that'll be 3.9. When you're doing these problems in ALEKS, make sure that you are paying attention to how many decimal places they want you to round to, because they'll often tell you round to the 10th place, round to the 100th place, the 1000th place. And so if you don't round to the correct number of places, they might mark your answer wrong. Now this next one, we've got a little bit of algebra to do before we start trying to solve for our x value here. This 3 needs to get onto the other side so that we can start getting this piece alone here. And I want to get rid of this 40 if I can. And that becomes 6. And now because I see an e here, I'm going to take the natural log of both sides. And remember, base is the same. The 6x can come out front. That'll just be 1. So I have 6x equals the natural log of 6. And then I can divide both sides by 6. Those do not cancel out. This is inside the logarithm, so it can't cancel out. Don't do that. And then x is equal to the natural log of 6 over 6. And I can type that in my calculator. And we get 0.3. I'll round to a few more decimal places. That way you can see some rounded to different decimal places. Let's do 3 decimal places. That'll be 2.99. Okay. All right, let's keep moving on to more examples. And here we have some more exponential equations. Again, there's no way for me to rewrite these in the same base. 5 and 4, there's no rewriting those into the same base. So I'm going to take the natural log, or I'll just do regular log this time again. onto both sides, and I need to move this out front and this out front. But be careful, because since these are multiple terms here, you want to make sure you put parentheses around it. So I have x minus 2 times log of 5 equals 2x plus 3 times log of 4. Now what's difficult about this problem is that I have more than one x. I don't just have one x that I'm trying to get by itself, I have a few. So what I'm going to do is I'm actually going to distribute here this log 5 onto the x and onto the 2, and same thing here. So this is going to become x log 5 minus 2 log 5 equals 2x log 4 plus 3 log 4. And every term that has an x in it, I want on one side, and I want everything else on the other side. So I'm going to subtract this onto this side, and I'm going to add this over to this side. I have x log 5 minus 2x log 4 equals 3 log 4 plus 2 log 5. And now I have an x that's a common factor in both of these terms. So I can factor it out. And now x is by itself, and all of this is just a number. If I typed that in my calculator, I'd get a decimal. This just represents a decimal. So I can divide that onto the other side, and I get x equals 3 log 4 plus 2 log 5 over log 5 minus 2 log 4. And that's my exact answer. I can type this in my calculator, but when you do, be really careful of order of operations. So I'm going to show you how I would type it in. I'm going to use a lot of parentheses. So I start my set of parentheses here for the numerator. And then I'm going to close that on the 4, plus 2 log 5, close that on the 5, and then close that for the top. So that's the entire numerator in a set of parentheses divided by the entire denominator in a set of parentheses. And that gives me negative 6.34. Now the next equation looks definitely quite different from the ones we were just doing, but I do notice that it follows a quadratic pattern. I have e to the x and e to the 2x. Well, let's do what's called a u substitution. I'm going to let u, and you can use any variable, it doesn't have to be u. I'm going to let u equal e to the x. Well, that would replace this with u, so minus 8u plus 7 equals 0. And if I square both sides, that would be e to the 2x being u squared. Well, this is just a quadratic formula, or a x method. 7 and negative 8, that'll be negative 1 and negative 7. U minus 1, u minus 7 equals 0. U equals 1, and u equals negative 7. Oops, positive 7. But remember, I don't actually care about u, I care about e to the x. So what these really are is u being replaced with e to the x. I have e to the x equals 1, and I have e to the x equals 7. So using that little u substitution helps us realize this is just factoring. You can do it without the u substitution if you want. And then I need to solve each of these. Well, I can take the natural log of both sides, and then that just becomes x, so I have the natural log of 1, and this becomes just x, and this becomes the natural log of 7. Well, remember, any logarithm with any base of 1 equals 0. So I have x equals 0, and I have x equals natural log of 7. So far, we've only been working with exponential equations. We haven't worked with any logarithms. These next few examples will be with logarithms, and so we need to be a little bit cautious because remember, we can't take the log of a negative number or of 0. So when I'm solving these types of equations, I need to make sure that whatever I get, I'm not getting something that when I plug it in will give me 0 or a negative. Now, looking back at the previous page, and what options we have here. Here it's if I have a log on each side. Here is if I have a log on one side and something else on the other. And so this example looks more like that. This one looks more like using the Snail Rule. So I have one logarithm equals a number. I can use the Snail Rule here. 2 to the power of 3 equals x minus 4. And now this is just solving a linear equation. 2 to the power of 3 is 8. And add 4 to both sides, and x equals 12. But again, I need to check my answer. So plugging in 12, 12 minus 4 is 8. Taking the log of 8 is not an issue. So there we go. Next one, again, logarithm on one side, number on the other. But the logarithm is not by itself yet. I have a coefficient of 4 out front. So I need to divide both sides by 4 before I proceed. Now remember, a natural log has base e, so when I use the Snail Rule here, I have e to the power of 2 equals 3x. And then getting x by itself, I would just divide both sides by 3. E squared over 3 equals x. Well, again, we want to make sure that plugging this in is okay. E squared is positive, divided by 3 is positive. A positive number times a positive number is positive. So again, not 0, not a negative, so we're all good. Now this next one looks like we have 2 logarithms, but we have a constant on this side. So before I can use the Snail Rule, I need to condense these because which one would I use the Snail Rule with? Would I use the Snail Rule here? Would I use the Snail Rule here? How do I know how to proceed? So I need just one logarithm on this side, so addition can condense to multiplication. So now it's one logarithm. I can go ahead and simplify this a little bit further. And remember, if we don't see a number here, that's base 10. So 10 to the power of 1 equals this. 10 to the power of 1 equals x squared minus 3x. And that's a quadratic equation, so we want to get it set equal to 0. I'm going to subtract 10 over, and I get x squared minus 3x minus 10 equals 0. You can use the x method or quadratic formula, whatever you prefer. And I get x minus 5 and x plus 2 equals 0, x equals 5, and x equals negative 2. Now we need to check our answers here. So plugging in 5, 5 minus 3 is 2, 2 is positive, so we're all good there. Plugging in 5 here, that's positive, that's all good, so this is an answer. Plugging in negative 2, oh, negative 2, that would be taking the log of a negative number, so I don't even need to check this one, it just has to not work in at least one of them. Now, just because this is a negative number doesn't make it necessarily not an answer. We can get a negative number here that when we plug it in isn't negative, but in this case, this one did not work. So, one more problem. And here we have the natural log of x plus 2 minus the natural log of 4x plus 3 equals a natural log. So going back to our list, now we have logs on both sides of our equation. Oh, there we go. Logs on both sides of our equation. So if I can get one log on this side and one log on this side, I can set them equal to each other. So I need to condense this side, and subtraction condenses to division. So I have the natural log of x plus 2 over 4x plus 3 equals the natural log of 1 over x. And when we use that property, if I have the log base b, so same bases, one logarithm, then that means these pieces are equal to each other, kind of like what we were doing here, where we set the exponents equal to each other. I have the natural log of this equals the natural log of this, so those two must be equal to each other. And now we have one fraction equals one fraction. This is back to solving rational equations. So I can use cross multiplication here. 4x plus 3 times 1 is just 4x plus 3. X plus 2 times x gives me x squared plus 2x. This is a quadratic equation, so I want to set it equal to 0. So subtracting 4x minus 3 minus 4x minus 3, I end up with x squared minus 2x minus 3 equals 0. Using the x method, negative 3, negative 2, negative 3, and 1. And I get x equals 3 and x equals negative 1. But again, with logarithms, we have to check our answer. So plugging those back into the original equation, plugging in 3, 3 plus 2 is 5, that's fine. 4 times 3 is 12, 12 plus 3, that's fine. 1 over 3, that's fine. So this one's good. Plugging in negative 1 plus 2, that's 1, that's fine. Plugging in negative 1 times 4 is negative 4. Negative 4 plus 3 is negative 1. Oh, that doesn't work. Again, just because this is a negative value does not mean it automatically doesn't work. It just happens to not work in this one. So x equals 3 is our answer. And this brings us to the end of this section.